So good afternoon, everyone. Thank you for signing up for our workshop. So my name is Hui Wang. I'm the Sim coordinator of monolithic and heterogeneous integration in EPIC. And I would like to introduce our workshop first. So our workshop will be 8 weeks long, including 4 technical talks. So today is the laser and scene introduction from our Sim director, Corbett. And then there'll be about the material growth and the laser design and the fabrication. We will then have 2 videos and discussion sessions. One is in the lab and one is in the clean room. So you get a chance to see what a real life will be like. And another session is a web-based simulation with one of our PhD students. It will use Python, and we will share the details about the installation and the menu before. And the last will be the PhD experience sharing session. We will have 5 PhD students from first year, second year, and third year. We would have small groups, so you have a chance to ask any questions you'd like to know about their PhD experience. And in the end, we will have a laser demo competition. So you could submit any formats. You could make a presentation about 3 minutes long, or poster, or any practical demonstrations about the laser using materials like Lego or Play-Doh or just the box, anything you could think, and for the general public. I will share the details later with you. So we will also have rewards for the top 3. And this is a schedule for the whole workshop. The details of the Zoom link will also be shared with you at least the week before. This is the time for that. And any questions?
All good, I think.
All good, great. So I finished with my slides. So now let's give a very warm welcome to our Sim director, Corbett.
Oops. Okay, so welcome to Tyndall, everybody, and I'm sorry that you're here virtually at the moment, but hopefully by the end of the summer you'll get a chance to come to see Tyndall itself. I'm talking today about a mouthful called Monolithic and Heterogeneous Integration Theme and Introduction to Photonics. Now, I guess you're all studying at university, so you're studying something like physics or chemistry or materials, but a number of you are probably studying electrical engineering or electronic engineering. And so that's a very important topic. And what we want to show in what we talk about now is that photonics is just as important, or will be just as important. And that in the future, there'll be courses called photonic engineering. And so I want to give you a flavor about why that'll happen. And one of the main things is, the application of photonics. In terms of electronics, you'll see in a moment that circuits are simply everywhere. So they're used in all sorts of different situations. But what's the situation with photonics? And what are the big applications for photonics? One of the really huge ones is solar power. Again, if you look back 10 years, you just said that's a really quirky technology, only used in the hottest place in the world and too expensive. But right now, across the world, solar conservation or conversion is the lowest cost of electrical energy. So it's really taking over in the US and in Saudi Arabia, in Europe, and it's coming to Ireland very, very soon. You might know there's many different planning applications for solar farms to be in Ireland, because we're obliged to do this to prevent carbon-based fuels being operational. So it's really cheap, and it's based upon a material called silicon, which is very good at converting sunlight into electrical energy. We work on another type of material called gallium arsenide, which is even better. It's 5 to 10% better. And when you put it together with multiple junctions, we can actually convert now under concentrated solar light, 45% of the energy that's in the light into electrical energy. So it's really a sea change in how we'll be going about things in the future. But if we generate energy with solar, then we're giving it all away when we go to displays. So you know that displays have had a long history since the first TVs. They are based upon the cathode ray tube. So electron beams in a vacuum onto phosphorus, which would convert the color. But in the 1980s, there was a big change where people moved away from that. They had the plasma displays, and then we moved to liquid crystal displays with backlit by halogen lamps and mercury lamps. Those lamps were then replaced by LEDs, and now we've moved to a new material called organic LEDs. We're looking at quantum dot as down converters, and the latest technology that's on the way and that we're heavily involved with is in making micro LED displays. So that's using semiconductors to convert the electrical energy into optical energy. So that can be done with much greater efficiency than all the other technologies. And so that's going to, we hope, dominate in the next few years. Cameras, as you know, have also taken off recently. The end of Kodak and film happened in the 1980s. And now you can get the most tremendous camera chips that are on your mobile phone. But the thing that sustained our activity at Tyndall over the last 30 years has been in communications. So that's the growth of the internet, where you can send vast amounts of information over optical fibers. That has required us to make lasers, detectors, and modulators in the wavelength range of 1.5 microns. So that's beyond the visible spectrum. The visible spectrum covers from around 400 nanometers to about 700 nanometers. So if we go to longer wavelengths, we first reach about 800 nanometers, where there's a lot of interest in communications there. But optical fiber, it turns out, has the lowest loss in the 1.5 micron range. So that forced technologists to develop lasers working at wavelength range to make modulators to send that data and detectors. Now, this has been our core activity, as I say, and the reason why you use optical communications is very clear, is because you can actually send a lot more information over a much smaller cross-sectional area than with electronics. And I'll talk about that in a moment. So, you know, we've got the mobile phone. That's obviously communicating using radio waves. It's also electromagnetic wave, but it's a much lower frequency. So in order to put all that information together, all the data is multiplexed onto fibers and sent around Europe on fibers, around Ireland on fibers, and across the planet on fibers. In fact, the first long distance fiber link from country to country was between Ireland and Wales back in the 1980s. That was 110 kilometers of fiber link without any amplifier between the two sections. So you could send light and detect it down the other end. And as I said, it's got a really extraordinary capacity for sending data. So on a single fiber, so that's a fiber has got a core diameter of about 9 microns. And if you think about microns now, the diameter of your hair is about 100 microns. So, you know, 9 microns is 1/10 of that. So it's a phenomenally small dimension. But that's the dimension that we talk about. But over that dimension, it of course has a cladding layer. You can send 172, this is a record, of terabits per second over 2,000 kilometers. So that record was done using what was called a 3-core fiber. So it's 3 cores within the single fiber. And that can take 5 billion simultaneous phone calls. And that's over a single strand of optical fiber. So really, it's a phenomenal amount of information that's been sent around. So that means we can all communicate. So during this pandemic, there was a seamless move to online communication because the infrastructure was there. So that we were partially lucky, or maybe it's because of our development that all of this has happened. So because of that as well, we've now moved away from having a computer at your desk. People are working more from laptops or from mobile phones because actually they're storing their data not locally but distributed in what's called data centers. And these data centers have huge requirements because they store obviously vast amounts of data, but they use a vast amount of energy. So in order to do that, use that energy, you need to cool your systems. So therefore, you need to move to climates where the temperature is quite uniform. So Ireland, it turns out to be a nice place for installing your data center. And so this is a picture of the Facebook data center up in Clonee in County Meath. And you see they've done a beautiful job in the layout, representing the Celtic motifs. But over here, you can see there's a ESB substation. And within a few kilometers of this location, there's the electrical interconnector between Ireland and the UK, which keeps the balance of power in the country. So if you look up any of these data centers, they'll tell you that in fact they are operating in an environmentally friendly way and not using any, they're using all renewable energies. And that's because they buy every new wind farm that's developed, and presumably they're going to buy the solar farms when they're developed. They'll take all that energy. But so then a few facts about these data centers. They cost 100 million euros to build, so they're vast amounts of infrastructure costs, but they only employ a handful of people when they're operational, because actually it's all run remotely. And so all the major tech firms have data centers in Ireland. Currently, people are saying that maybe 10% of the world electricity is used for handling of information. So maybe it's 3 or 4% that are used in data centers. But in Ireland today, 20% of the electricity is being used by data centers. So to know how much energy has been used, you try and work it out. And the EirGrid have a very nice app that tell you what the current use of energy in Ireland is. If you look it up now, I think you'll find it something like 4.5 gigawatts of energy is being used during the daytime. At the nighttime, it's about 2.5 gigawatts, and just about 1 gigawatt is in these data centers. And so it's a big issue for Ireland to decide whether we're going to have these data centers, but they're not going to go away. And where it comes relevant for us is that all the connections to the data center in terms of information is coming through optical fibers. And within the data centers, increasing amounts of the information flow is over optical fibers. So here's a screen grab of some data center, and all of these blue and yellow and orange cables all are representing are optical fibers. So instead of electrical wires connecting the instruments and the servers, there's optical fibers connecting the centers. So this is a huge use of light, and it's really changed the light industry. Because before light, you could charge quite a lot of money for your light source or your light detector, because actually you only used a few of them. But now that you need to use vast amounts of them in data centers, and they say 20% of the cost of a data center is associated with the optics, they need to be more consumable products. So you've had to industrialize all of these activities. So the things that these fibers connect to are going to be transceivers. They're going to receive the data, they're going to convert it into electrical energy, and vice versa. So there are going to be two ways of communication. So as I mentioned now, that the data center is a giant cross connect. It's really just connecting pieces of information. So when you look for your video, it's got to find it within the data center and bring it back to you within, instantaneously. So most of the energy and therefore the flow of information is actually within the data centers themselves. And not only are there one data center, but these companies are having to have multiple data centers that they connect with each other. So 14% of the data center traffic is that way. So while you might think you're not using a lot of energy in order to look at a video or something, it's inducing an awful lot more data flow within the data center. So what's really key, of course, is to lower the energy consumption per bit of information. That's the end game. So if we can reduce that, then we're going to reduce the amount of energy consumed in those data centers and cut the energy bills. So if we could cut the energy consumption per bit, maybe we could halve the energy consumption. So that means that you've got to figure out how that information is flowing within the data center. So it's an electronic chip that's going to do the cross connect. But once it's done the cross connect, the information flows goes through fibers, and these are working at these 400 to 800 gigabits per second. So phenomenal amount of information flow that's rushing out of these chips in order to do this cross connect. So there's a huge effort and a huge industry creating the optical components for these systems. So let me just switch back now to talk a little bit about electronic circuits and how they have evolved, because maybe we can use that as a mirror to see how photonics will evolve. The first transistor was in around 1947 based on germanium. It took till 1963 to the first sort of circuitry, so it took a while to get going. But now in 2019, with 10 nanometer nodes, you have 100 million transistors per square millimeter on these huge record size plates of silicon. And we know that the laser itself was discovered, the semiconductor laser was discovered in 1962. And yet today we don't have an electronic or a photonic circuit technology that's available to everybody. But that's about to take off, I think. So there's been an exponential growth in the number of transistors per wafer, whereas photonics is stuck here. So this is in 2015. So we are on a growth curve, and that's what you're going to see over your lifespan. If you look at an electronic chip, you'll find it's got layers of transistors down the bottom, but the vast majority of the cross section of a electronic chip is made up of wires. So these are all these plugs here are connecting between various levels, somewhat like New York was in the early days of the last century. So all the wires were connecting one thing to the next. So there's a huge bottleneck when it comes to connecting items, and that's where photonics really comes to its own. Electronic circuits also are built upon building blocks. So if you look at a circuit, it's got a small number of unique elements which you basically put together in a circuit to make your full complex system. So you've got billions of transistors on a circuit. How can you even handle that? How can one human actually do that? And the reason they can do it is because it's built up of sub-elements, and these are circuit building blocks. So you assemble them as you would like a Lego system. And as technology evolves, the people don't need to know how a transistor works in order to build a very sophisticated circuit. So, and it's going to be the same with photonics, where we're still stuck at the point where people need to know the technology, and they need to know the physics of how a laser works. So these circuits cost phenomenal amounts of money, but because it's done in such volumes, when you divide it all up, it costs cents per circuit. So that's why your mobile phone is at a cost that you can afford. because the various circuits that are on that are all produced at a very low cost. So these circuits are made in foundries. So they're made on wafers, which are a piece of silicon. It's grown in a sort of cylindrical sausage shape, and they're sliced into wafers. And then the technology is done on the wafer surface. So the interesting parts of photonics, or of electronics even, are on that surface. The fabs are, for example, up in Derry, Seagate, are making magnetic wafers. In Limerick, Analog Devices are making sensor wafers. And in Leixlip, Intel are making state-of-the-art electronic computing wafers. So it goes back then to electromagnetic radiation. And as I mentioned, you've got electrons. Electrons are moving in the circuit, and they are causing the switching action. But when you go to a communication, when you want to send a signal from A to B, you inevitably send it using an electromagnetic wave. And the wave, of course, can vary in frequency, from very high frequency gamma rays down to very low frequency DC, like you convert power over the country. We're interested in the visible part and the infrared part of the spectrum, whereas the people who work in radio are interested in gigahertz. So if you've got a phone, your phone is working at probably a 2 or 3 gigahertz signal. So it's about 10 centimeters in wavelength is what the radio waves. We are working, as I mentioned, in the UV to near IR part of the spectrum, typically 1 micron wavelength. So that's much shorter than this one here. And the frequencies are correspondingly higher. So they're 100,000 times higher. So that ultimately means you can send 100,000 times more information in the same with the same system. You also have other features of electromagnetic waves. Obviously the intensity of the field, the wavelength of the light, the polarization, and even the phase of is available for information signaling. So there's many limitations for electronics for signaling. So when I talk about electronics, I'm thinking about, well, you send a signal over a cable, so over a pair of wires. So you think, of course, you're sending electrons over that wire. You've got a current going back, but actually the current travels as a wave. It travels as an electromagnetic wave. And so that's why when you go to higher frequencies, you have to use coaxial cables, because basically the electromagnetic wave has got a large wavelength, and it escapes from the wire, and it starts to interfere with the adjacent wave. Also, the current is confined to the surface of the metal, and that means that the resistance goes up. So photonics has multiple advantages. You've got minimal interference between light, comes into your eye, crosses, it's not a problem. You can do wavelength division multiplexing, where you can put red, green, and blue together, and you put all the different frequencies together. So that's how we can send the information over the internet. We've got a remarkable hose pipe of sending information through a certain area. So if you think of those data centers, the information is coming in through fibers, and the flux of information flow is data flow is really phenomenal compared with that of electronics, because of this interference problem, because the waves interfere with each other and they distort and they create noise. And the other big thing, of course, is at the energies of infrared and visible light, we are essentially detecting photons. So it's one by one. You can count the piece of energy in, and that leads to huge advantages. I mean, the advantages are so significant that it's easier to send information by converting from electronic domain to the optical domain to the electronic domain than sending it in an all electronic fashion. So all communication now, as you can see, is done in what we call the optical domain. So then to think about some of the components that we work with, well, light generation is really important. How are we going to make the light signal that's going to be the the energy that's going to contain the data that you want. So light comes from a hot body like the sun, or from a plasma, or from bioluminescence, or from just heating. So this is a version of the sun. But of course, what's happened in the recent times, of course, is we can do it from a semiconductor. So that means we can do it in a very controlled manner. So we need what's called P-type semiconductor, where essentially the current transport is via holes, and N-type semiconductor, where the current transport is through electrons. And at a junction between those two, the recombination takes place. And depending on the material that's at the junction, you can generate different colors of light. So to make our lasers, we start also with wafers, just as in the silicon industry. So this wafer, unfortunately, is much smaller. It's 50 millimeters to 150 millimeters in diameter. It's got a thickness of about 0.5 millimeter. And we take it to a machine and we grow layers of material upon that wafer. And these layers are of a thickness of a few microns. So very, very thin layers on top of a thick substrate. But they contain all the materials that you need to create a laser. So we then have to do some processing on that wafer to create waveguides, which will guide the light in a pencil-like format along the crystal surface. That light and that width is of the order of microns. We then have to cut them into bars and to coat them. And then we can test the device, putting it, in this case here, it's a red laser. It's tiny, its dimensions are in thickness 100 microns, so as I say, the diameter of hair, and a length of up to, say, 1 millimeter in length. So it might be 200 microns to 1 millimeter. But within all of that stuff that's happened there, there's some very, very important aspects. So the bit that does the light generation is composed of very thin layers of a few nanometers in thickness. So between 4, 5, 6 to 10 nanometers. And they're sequenced upon each other. And they're the most important thing of all for the laser. If this material is not of sufficient quality, then it won't work. And these are all grown and engineered, for example, at Tyndall. So that's the way we can make a laser. But how can we make a circuit? Why are there no circuits at the moment? And how will they work in terms of size? Well, one of the different issue or difficult issues compared to electronics is the size of the photon is much larger. In fact, you can even say what the size of the photon is. It's lambda over 2n. Whereas with the electron, actually nobody can tell you how small an electron actually is. It's a point object from all experiments. So the photon is lambda over 2n. So if we got a device that's working at 1 micron, then it's going to, and the refractive index, which is a very important parameter for optics, we get to around 200 nanometers. So that's a very tiny number, but compared with electronics, it's a very large number. So the latest generation of electronics is working with dimensions that are of the order of 5 to 10 nanometers, so much, much smaller than this. The other issue is that the best photonic devices, all of these devices here, all require different structures. Whereas actually with a transistor, you can make everything. You can make a transistor behave like a resistor. You can make it behave like a capacitor. So they can all be made from the same things. But that's not the case in photonics. And these materials are also very sensitive to defects. They're also based upon materials I'm sure you've never heard of before, indium phosphide and gallium arsenide. You see, first of all, that they're binary elements, whereas silicon is a single element. So it turns out then, of course, with a single element, you can make much better crystals than you can with 2 elements, because there's more types of defects in a 2-element system. You also have to have these waveguides and combining with electrical functions. So the components that you would have on a photonic circuit are quite varied. So that's also a difference. we have waveguides, and that's probably what's most important of all. Then the waveguides are, how small can you make a waveguide? Well, you need to confine the light in X and Y to go along the plane in Z, if you like. And so there's the photon is a field as well. So it's got a certain spread, and you need to confine it. So you need a high index material surrounded by a low index material in order to confine the light. So you can make a wire for light. So do you make the light go along a wire? And one of the problems with photons also is that the curvature of the wire is very significant. You have to be very gentle with photons. If you go around the corner too sharply, the light will splay out and you'll lose light, and therefore you lose energy. Also, the light has to go along the waveguide. It can't be scattered. So the edges of the waveguide need to be really perfect in order to not have loss. But because the light senses outside the waveguide, because it's got a component that escapes, you can now put it together with another waveguide, and they can cross couple. So there's a coupling goes back and forth between these. So you can cause light go from this waveguide into this one, or to go 50-50. And you can do this in various ways, multi-mode interferometer, and you can make gratings on your device, and the grating can act to couple between the in-plane light and the out-of-plane light. So there's a whole load of passive components, which I mean is that they essentially guide themselves according to the wavelength of the light and the size of the dimensions of the object that you created. When we have to have active elements as well, the lasers that I've just shown you, which can also act as amplifiers, detectors, modulators, plus a load of components that people still have not figured out exactly how to do them in the most effective manner. And these circuits that we're coming up with, well, as I mentioned, for data centers, that's a huge driver, because we know what we want there. The industry says, provide me with a component that can deliver 100 gigabits per second on a channel, and they can be used in supercomputers, fiber to the home. As you know, there's a broadband rollout. They need transceivers, to send the information up and back. 5G that is coming now will have a huge requirement on sending that information back down to the customer. Automated vehicles now have started to become a reality, and LiDAR, light distance and ranging using lasers, is one of the technologies to avoid collisions. But there's loads of other ones, and people really, they're only starting to come up with these ideas now, because we're not sure, because we haven't had the technology. We haven't been able to go off and dream of these, because we needed the infrastructure. And that infrastructure has come actually from the same silicon industry. So because silicon is such a mature technology, that's the platform on which things can be made in volume, so truly manufacturing. So this can bring down the cost of everything. And the configuration for a circuitry, for photonic circuitry, that's going to win out is this configuration here. It's very simple. It's a silicon substrate. It's got a buried glass oxide, so it's a silicon dioxide, on top of which you've got a layer of silicon. And that layer is extremely thin, 200 nanometers thick. And that's going to act as the waveguide. But of course, you're saying silicon, if you know silicon, you know it's a gray material. It's the same material that's going to absorb the sunlight. So how are you going to send signals through that silicon layer? Well, when you go into the infrared, silicon is transparent. Just like if you look in the UV, you find that glass is absorbing, but in the visible infrared, it's transmitting. So the same with silicon. In the infrared, 1.3 microns or 1.5 microns, silicon is pretty transparent. And because we have all this technology to make and process silicon, this turns out to be the perfect platform for waveguiding. So one of the huge problems is, of course, that silicon has no laser. You can't make a laser out of silicon. So this is an example here of a photonic circuit. But while you can't really see what's going on here, what I can tell you about is the dimensions. It's 2 millimeters by 4 millimeters. And you can see that the number of components in this is the order of 15 or so component. If this was an electronic circuit, there'd be say 100 million or 1 billion transistors within the same footprint. And what this circuit is doing, it's converting light from a fiber into a photodetector to record a signal. So it's manipulating the light in terms of its polarization, its phase, and in terms of the signal that's obtained. So a very, very simple circuit, and this is a state of the art now. And you can see these are metal tracks, but underneath there, which you can't really see, are the black lines that represent the waveguides. This, for example, is another circuit which is obviously a bit more complicated in layout, but what it is, it's a complexity of interferometers. But this circuit here has no light source. It's like you haven't got the plug for your system, so you've got to plug it in, and to plug it in, you have to shine light in somewhere. So you need some place to couple light into your circuit and some place to take light out of your circuit. So this is it's not quite entirely what you call passive, but it manipulates the light. So in fact, it generates light here because of a 4-wave mixing process, and then it distributes those photons. This is for quantum computing. But you can see then circuits start to become fairly complex, but they're all built up of given elements. And that's the technology that we need to do. Now, just to mention what we do at Tyndall, one of the areas that we work on Tyndall is trying to integrate that laser, that light source, onto the silicon. And we're using a technology where we create essentially suspended devices. So these are devices that can be grown on their starting indium phosphide substrate and then transferred to a silicon substrate. So this is a picture, optical microscope of a laser. It's about 600 microns long. It's got gold pads for the P contact and the N contact, and it's held and suspended in place using a polymer material. So we can take those individual devices and we can put them onto a silicon circuit where we can shine the light from our device into the waveguide. This is quite a tricky thing to do, because actually the dimensions here, as I said, the silicon waveguide is 200 nanometers. Our photon inside the semiconductor is more like 1 micron in size. So we have to shrink it down in size by gently manipulating the light from the waveguide core in our laser into the silicon waveguide. And then we have our light coupled in. So that's one strategy to get laser light onto a silicon circuit, so to make the transistor of the silicon photonics. You can also couple the light in an evanescent way by directly bonding the semiconductor material to the silicon material. And then you have to gently manipulate the light from the semiconductor material to the silicon. So the silicon is represented in red here. And you have to have these gentle tapers where you squeeze the light ever so gently from one waveguide to the other. And it depends very critically on the dimensions that are on your structure. So it needs very, very precise control in order to guide and coax the light to do what you want it to do without excess losses, because those excess losses ultimately lead to the heat and those data centers overheating. So within our theme, which again comes to monolithic and heterogeneous integration. So the heterogeneous refers to the joining of the two different materials together, as I just showed you in the last slides. Monolithic is where you try to build the entire circuit from the one material. And that's ultimately limited for indium phosphide because of the sizes of the wafers and the different functionality that needs to be done. So we think that heterogeneous integration is going to be the main way forward. But within IPIC, we are very, very lucky to be what's called vertically integrated. In other words, we can go all the way from dreaming up of new materials to growing those materials in a layered structure, to designing the devices, making the devices, and then combining it with the silicon part, doing the integration, testing, verification, and ultimately making demonstrations. That's our main goal in the program. We have a team of PhD students, researchers, and investigators. So we've got a very big team where from everywhere, representing all of society, I would say. And the research environment, which I think you'll get a flavor of during your time at Tyndall, it requires a commitment from the student and from Tyndall. So we'll support you, but you have to also come and get involved in the research, because our output is in new knowledge. We try to create new types of devices or materials, and we want to communicate that to the world. We want to make high impact science by attending major conferences, which of course has been missing for the last 18 months. But we also want to have collaborations and work with across the board. And ultimately, of course, it's a springboard for a job in industry or academia. And you can do this in Cork to anywhere in the world. So one of the nice things is that recently, there's been a growth in the number of companies, photonics companies in Ireland, and particularly in Cork. We have Rockley Photonics who come here. We have Facebook who are developing AR and VR. We have Accelerprint who are doing the transfer print technology. And we have Sensel who were bought out recently, who are doing avalanche photodiodes. So it's quite a vibrant place for photonics. And so in my final slide, what I'm hoping for photonics is that really there's a proper evolution to photonic integrated circuits. It's been very, very slow in developing, but we can just see the need for this technology. And of course, once that happens, then all the shackles are off, and people can really start to dream of what are the really neat circuits that can be done. So we're essentially doing what's obvious, in terms of communications or in sensors. They're almost obvious, but there's quantum communication using photons to do the qubit. But there's loads of things that we've not really appreciated, and that would be the big application. And can we go deeper with optics and use it in really clever ways, using all those other properties of optics? The coherence, for example, is a very, very important property that you can manipulate, especially with these circuits. And of course, we want to have a knowledge generation through IPIC and to add to this photonics industry in Ireland. So with that, I'll finish up, and I'll be happy to take any questions that you would have.